All right, vi fortsätter. Så en summering utav det här konceptet med ett lager. Let's start over in English again. So a summary of where we stand. So we have talked about layers, and layers is a set of related communication functions that provide services up by using services below. So this sounds great, but you know, the devil is in the details. So how do we define and group these related communication functions into a layer? And how do we split the functionality of the network between the layers? And how do we specify services? Okay. So guidance to this is applied in forms of what's called reference models. So there are two main reference models that we will talk about in this course, and one which is called the Open System Interconnect OSI model. Okay. So this one has 7 layers. So the designers of this reference model said, okay, we need 7 layers, so 7 types of groupings of functionalities. It's a very, very influential model, but is not used in practice in the sense that the protocols that were designed for this are not used at all, as I understand it. But then there is this internet reference model, which has 5 or possibly 4 layers. The reason why it's 5 and sometimes 4 is because people basically, what happens was that this model or the protocols were evolved before one started to think very strictly about layers. Okay. So the internet, as we know it today, has evolved from some research networks that were designed in the 60s, and people didn't then think much about layers and so forth, but they basically put together protocols that made it work. And afterwards one tried to say, okay, well, this protocol is in this layer and this is in this, and one doesn't really agree upon the number of layers. If you Google this, you will sometimes see 5 layers or 4 layers. It's empirical in the sense that it has evolved through engineering during the years, and it's heavily used in practice. Okay. But nevertheless, it's meaningful to talk about the OSI model, even though it's not used in practice, because it's much cleaner, and the principles of layering and services and so forth are well developed here. While the internet model actually breaks some of the rules sometimes, and then it becomes a little bit messy to talk about this. So we'll talk about the beautiful OSI model first, and then talk about the messiness and the practicalities in the internet model later. Okay, so let's start with the OSI model. 7 layers. Remember, the lowest layer is called number 1, and the top layer is called number 7. So the question is this something that you guys need to memorize for the exam and so forth? And I would say not necessarily, but it doesn't hurt. It's actually very good to learn this by heart. You know, so write this down on a piece of paper, read it before you go to bed. In the morning you look at it, and you know, at some point this is natural to you. So it might be worthwhile learning this, and also to learn what is the main functionality of all of these layers. So the physical layer is responsible for transmitting bits over a physical channel. Data link is to transfer something called frames. We will talk about all these concepts later on, so don't worry about if you don't understand them right now. But basically, the physical layer transfers bits, data link transfer frames, network packets, transport messages. Physical layer is over one physical channel, data link is over a single link, network is over several links after each other, and then the transport is the first what's known as an end-to-end protocol. So it resides in the host devices, so at the edge of the network, so provide end-to-end functionality. And then we have the session, presentation, and application layer that do these type of more refined services. But we will already now go on and say that we will merge the top 3 layers into one layer, because this is typically how implementation are done. And as time evolved, it turned out that the session and presentation layers were pretty thin. They didn't add too much. So typically one lumps the layers 5, 6, 7 into one layer that we call the application layer. And it's still numbered 7 for some reason, right? So it's funny here, you go from 1, 2, 3, 4, and 5 and 6 is merged into 7. So that could be sometimes confusing then, because then layer 7 is using the services of layer 4, right? You know, which sort of breaks our current thinking about things. Anyway, so if we go back here and say you don't have to perhaps memorize all of these, it doesn't matter if 6 presentations above session or session. So basically everything which is here is the application layer. So that helps a little bit in the number of things to remember. Okay, any questions? No, well, let's continue then. Okay, so now let's talk about messages which are flowing between protocols. So remember that protocols are talking virtually with each other on like horizontally like this. So HTTP here and HTTP here, they transmit messages between each other, and these are HTTP messages. TCP, which is on the layer below it, transmits TCP messages back and forth. So one can say that in general, a protocol message has a certain structure. And this a protocol message typically consists of 2 or maybe 3 parts. 2 main parts. One which is a header, okay, and this contains control information, address, sequence number, length fields, and whatnot. So if you remember this, okay, let's go do examples a little bit later. So this is something which is meaningful to synchronize and keep track of things in this the interaction between these 2 protocols. But then there is also some payload or data field, and this is what's carrying the data from the layer above. Okay. So and sometimes there is a trailer also with some control information, typically check bits for error control purposes or some other control information. Okay, we'll get into that in a second. Anyway, so this is a message, and if we think we have time along this axis, we have a number of bits here, right? So we have some 1 0s 1 1 1 1 0 1 some bits, and these bits we got from the layer above. So this is what the layer above told us to transmit. The layer above possibly also told us where to send this, which we addresses and other information we put in here. So this is control info, and this is generated by the protocol itself, okay, for its own internal use. And then here at the end here, we can think of this as also control information. Okay, it's also needed for the protocol to function. So this is actually the data which was requested to be transmitted, and this is some control information, some overhead which is needed for this to work. Okay. So if you think of this as maybe like when you want to send a mail, regular snail mail. So you write your message on a piece of paper, you fold it and you put it into the envelope, and on the envelope you write the addresses and put the stamp on it, right? The address and the stamp is not meaningful for the recipient of this. It's the message which is important, and the message is contained inside the envelope. right? So let's look at this when we have a protocol stack like this. So at the transmitting node, this one for instance, headers and trailers are appended as the packet travels down the stack. This is called encapsulation. So suppose the application program would like to send some data. Okay, so this is the application software would like to send some data from this node to that node. Then the application software uses the application layer protocol. So this data is then pushed down like this, together with some control information on where this should go. The application layer protocol adds its header to this. So then this is now the message which is transmitted between the application layer protocols. Okay. But the application layer uses the services of the transport layer. So this message is actually pushed down to the transport layer. And from the transport layer's point of view, everything from here to here is data. It's data you got from above, right? So the purple and the blue here is payload from the perspective of the transport layer, right? And the transport layer then adds a transport layer header to this. And then the process is repeated. This data is then pushed down. And from the network layer's point of view, everything that it got from above, that is the transport header, application header, and application data, is payload. Okay. And then it adds its network header to this. And then we continue down to the data link layer, which does the same, adds its header, typically also a trailer, not always, but typically like this. And then this is then fed down to the physical layer, which just sees these as bits, which then transmits this over the physical link to which this physical layer is connected, using a radio channel or Ethernet cable or something like this. Okay, so this process is called encapsulation, when data flows down and it's wrapped into bigger and bigger units of data, almost like you think of a series of envelopes. So if I'm a layer, I get some data above, I put that in an envelope and then write addresses and whatnot on this envelope. That's my header. And then I push it down. Then I get an envelope from above and I put my other envelope on top of this. It's like this Russian doll, if you remember. You know, it's like a doll, all encapsulated in one thing. Okay. And at the receiving end, once we go at the receiving end, say, so the data goes down here, encapsulated, and then transmitted over to the receiver here. And as data travels up here, these things are stripped off. So the physical layer put this up into the data link layer. The data link layer inspects its header, its trailer, and if everything is okay, it strips this off, deletes this, and then push the remaining things up. And the remaining things is everything, you know, it's like everything goes up like this. And then what the network layer basically then inspects the network header and then say, okay, is everything okay? Yes, it is. Then we strips that off and then pushes these things up like this. And then it continues like this. And this is called decapsulation. You know, encapsulation as we go down and decapsulation as we go up. So this is the principle. And the idea here is that a protocol on a certain layer here never, let's do it like this, it's even cleaner here. So the application layer protocol never uses the application data in order to do its task. Okay, so this is just seen as some, bits. I have no idea about the meaning of it, and even if I know the meaning of these bits, I'm not going to use that in order to do my job, right? So it's like what comes from above is meaningless bits for the protocol. It's just things that needs to be transferred. So that's an important principle here. So all information, how this application layer protocol talks to this application protocol, inform each other about different things, is covered in the headers. That's where the control information is. Okay. Questions? This is one of the key concepts in the course, capsulation and decapsulation. It will for sure show up on the exam. Okay. So, a little bit now about how a protocol works. Okay. So, remember now that the nth layer, say layer 4, is then interacting with layer n in some other node and provides a service to the layer above it. That is to layer n plus 1. So, here we have layer n plus 1. Okay. So if this is 3, for instance, this is 4. Okay. The communicating entities here, we can think of these as 2 different software programs running at 2 different machines, at 2 different nodes in the network. Okay. They are running in the same layer but at different nodes, and these are called peer processes. Okay, peer means jämlike, like it's on the same level in the hierarchy. Okay, so these are peer processes, 2 different software programs, and they're communicating with these data units. So layer n peer process uses a set of rules and conventions called specified by this protocol, and they are communicating by exchanging data. And the name of this data units is called protocol data units. So, PDU. So this is an important term, and it's good to know what it means. It means the data that goes between one protocol entity and another protocol entity in this horizontal fashion, which is virtual communication, right? We know this. But anyways, so the structure of this layer n PDU consists of some data, and this data was provided from above, and then some header which is generated by the protocol itself, the protocol entity itself. Okay, so communication between these peer processes is virtual, right? So this communication goes like this, is only logical or virtual. It's the physical one goes down the stack and then up the stack at the end of the same. But anyways, so it's virtual and actually then therefore indirect. So layer n plus 1 transfer information by using the services below it. So if layer 4 wants to transfer some information, 2 protocol entities at layer 4 wants to transfer information between them, they're using the services of layer 3. Services are available at some logical point called a service access point. And these service access points have unique identifiers. You can think of them maybe as addresses. So, for example, HTTP, which is an application layer protocol, passes information to and from a TCP process, which is below it, through a specific transport layer service access point called port 80. Okay, so Okay, so we have a web server process here which using HTTP. Okay, and then it transfers its information back and forth through this thing called the port, which is a a logical thing in this architecture. Okay. Now each layer passes data and control information to the layer below it through this until it reaches the physical layer, and then the bits are then transmitted. So data then received from the layer above is called a service data unit. Okay. So this is the second thing which is important. We have the protocol data unit, PDU, and then we have the service data unit, SDU. And service data units are encapsulated in PDUs. Okay. So probably at this moment, if you haven't heard these terms before, it's a little bit confusing. So let's make an example of this. And if you understand this slide when it's done after all the animations, you have come a long, long way of understanding protocols and layers and so forth. Right? So this is a quite important slide. So we'll take some time to go through it. Okay. So we have layers here, and maybe this is layer 4 and this is layer 3. I don't know. For example, right? So what we have here is we have these peer processes that resides on different layers. So if this is a layer 4, this could be, for instance, TCP, right? And if this is layer 3, this could be, for instance, IP. But just as an example, right? Then these entities are exchanged in protocol data units, but this communication is virtual. The actual communication goes down the link, and it goes through the boundary between two layers through this service access point. Okay. So a protocol data unit that needs to go from here to here. Okay, then we have this protocol data unit. Okay, and this is, in this example, this is a layer 4 PDU. Like this, okay? So it needs to go from TCP here to TCP here, for instance. Okay. So what is happening is actually that this is the virtual way it goes, but the physical way it goes down like this. So it goes down to the service access point, and then it's transitioned into the next layer. Okay, so here's the first thing. As we go from one layer to another, the same bits, the very, very same bits, are either a layer 4 PDU or a layer 3 service data unit. Okay. Same bits. Okay. Two different names of exactly the same thing. Okay. So as these protocol data unit from layer 4 goes down to layer 3, it becomes a layer 3 service data unit. Okay. Layer 3 encapsulates the service data unit. Oops, that was a badly drawn arrow like this. Into its protocol data unit, and then adds its header. Okay, so this is now the layer 3 PDU. And this is a little bit messy here, but this is the layer 3 service data unit. Okay, so that's the functionality of encapsulation. As data comes down, we add headers, and this is called encapsulation. Okay, next thing to do is that, of course, oops, what happened? This is virtual communication, so this is actually then pushed down here. So this is the layer 3 PDU, and then goes down to layer 2 here. and then becomes a service data unit in layer 2. Headers are added and so forth. So this process is then completed. Now at some point this protocol data unit, if everything goes well, is pushed up at the other side. Okay, so it went down here, and then hopefully it was transmitted up here, and hopefully it's the same bits. Okay, what happens now? Well, we see here that now actually this protocol data unit has now virtually appeared here, but physically it went like this. And then what is happening is that we strip off the header, and then we have the service data unit, which we then push up. At the other, it just changes name, it's the same bits, comes up here, and then we see that we have enabled now virtual communication of this protocol data unit, like this, by using the services of the layer below it, which in turn use the services of the layer below it. So we do encapsulation as we go down and decapsulation as we go up. Questions? No? Okay. Again, this is a great slide because it has a lot of information in it. And if you stare at it until you figure out how it works, you're in good shape. Right? Okay. Now, this protocol data unit, this entity here is then looking at the protocol data unit and then decides on what to do. And it decides to transmit the message back in the other direction. So what happens then is that we go through the same process but in reverse order. So this protocol data unit is then transferred down, it becomes a service data unit, it gets encapsulated with a header and then transmitted virtually this way, which means physically it's transmitted this way. And then it appears at the receiver here, it gets decapsulated and then delivered here. And therefore we have enabled the virtual communication horizontally by going down, across, and then up. Okay. So what is typically confusing here, I think, is that we have two names for the same thing. Okay, so that's important to remember, that something which is a protocol data unit on layer 4 is a service data unit on layer 3. Exactly the same bits. So that's one thing. And then the notion of encapsulation and decapsulation is important to recall. So this service data unit is encapsulated into a protocol data unit, which is then decapsulated into service data unit before it's pushed up. Are we cool with this? Or any questions, confusion? Now would be a great time to ask questions. Okay. Again, I cannot overstress the importance of this slide. So if you have this figured out, you'll be in good shape. Okay. Now, into some details here. These protocol data units have names. So sometimes it's important to associate a particular name with the particular layer's protocol data unit because it makes it easier to talk about it. Sometimes it's not so important. But I don't know, that's strange. It was still okay, anyways. So on the application layers, these protocol data units are called messages. On transport, they're called segments. On network, it's called packets. On link, it's called frames. And on physical layer, it's called bits. Okay. Is this super important? Not really, except that it gives you clues when you read documents. When they talk about packets, if they talk about segments, what they talk about is protocol data units at transport. You can infer that by the use of segment. Okay, and the same thing with frames, for instance. Now, packets and messages are used in much wider context, so you cannot be so sure about this. And as a matter of fact, as soon as we talk about the block of bits, we will use the name packet or sometimes frame. Right? So we will not be very strict about this in the course, but this is the way it should have been called, I guess. And then reality is also more messy in these models. So sometimes a physical layer, for instance, is not working on individual bits, but rather on blocks of bits. So Wi-Fi, for instance, do this. So again, we know this as engineers. There is a model of reality, and then there is reality. And there is not, a model is not a 100% accurate description of reality. It's a simplification, but the simplification is actually much easier to talk about and analyze and design for. Okay. Now, we have connection-oriented and connection-less services, and this is also, I think, confusing concepts. So let's see if we can spend some time on this. So if we have a service provided by layer n to layer n+1, that service could be connection-oriented or connection-less. Could be one of the two. Connection-oriented, for instance, TCP, is something similar to what we talked about circuit switching, where we, before actually transmitting any data, we establish a connection from node A and node B. If you remember, when we wanted to request this web page, we established a TCP connection before we actually requested the web page and before we got the web page. Okay. So a connection-oriented service then creates a logical connection between the layer n service access points at the end nodes, allocating buffer, agreeing on transmission parameters, and so forth, before any actual payload is transmitted. Then, after that, it transmits service data units that it gets from above. And when the layer above says, OK, I'm done, or there is some timeout or something like that, then the protocol cleans up the resources or releases them. So tear down the connection between the communications when the session is done by releasing buffer, allocated resources, and so forth. Okay. So these are connection-oriented, but there is also connection-less ones where we don't do this, where we simply transmit the data without checking first if there is a destination or whether the destination is ready to receive something. So we can think of this as a connection-oriented, almost like the telephone network, where we lift up the hook, we get some acknowledgement from the network, we type in the telephone number, there's a ring signal on the other side, the other party lifts up the hook. Okay, we establish a connection, and the network assigns resources for maintaining this connection. When we're done, we put down the hooks, and then the network resources are released for some other call. Okay, so that's connection-oriented. Connection-less is like when I send a telegram or a snail mail. I write my letter, I put it in the envelope, and I put it in the mailbox, not knowing if that there is somebody at this address that I just put down. I just hope that that is the case. Okay. So the connection, this type of service, if it's connection-oriented and connection-less, doesn't really depend, does not necessarily depend on the lower layer service. So TCP, which is connection-oriented, is actually using IP, which is connectionless. Okay. So one does not imply the other, right? Any questions on this? because this one could be confusing, right? No? Okay, we continue then. Let's see. I don't know. Okay, let's see. Here we go. I don't know why this is popping up. I'm sorry for that. I can't get rid of it. Some more details. We have something called fragmentation and reassembly, or blocking and unblocking. Segmentation and reassembly. There are many names. But what it is that we have a layer, and maybe can impose an upper limit on the size of the data block it can transfer. So, for instance, if I'm a layer, I can tell the layer above, okay, you can only send me data at most 100 bytes, or at most 1500 bytes or something like this. You cannot send me 3000 bytes or a gigabyte. You have to, the messages, I can handle messages, but only up to, say, 1500 bytes. Okay. So what happens then is that if the layer above me would like to provide a service to its layer above it, not having that type of constraint, maybe you would like to transmit a gigabyte of data in as one message. Okay. So, or another way, if I'm a protocol entity, the layer below me can only transmit 1500 byte messages or packets. I get 1 gigabyte from above. What can I do with this? Okay, I split it up in 1500 bytes chunks and transmit these individually. At the other side, my peer process gets these 1500 byte packets and buffers them and glue them together to form this gigabyte message before sending it up. Right? So the process of splitting a large packet, large message into smaller pieces is called fragmentation or segmentation. 2 words for the same thing. And when I get this, it's called reassembly or desegmentation. Okay. So is this clear? Yeah. So, which means that, yeah, okay. And what happens here is like you get a big service data unit, you split it up in many protocol data units, you transmit this individually, and then everything is glued together at the receiving end. Okay. Aggregation and deaggregation is the opposite almost, right? So if I'm a protocol entity, the layer below me can say, okay, I will transmit messages which are at least 1 byte long. Okay, you cannot just send me individual bits. I want them at least 8 bits long. And actually, I want them in chunks of 8 bits. Okay, so what we can do then is that if I get bits from the layer above me, I know I cannot send them directly down. I need to aggregate at least 8 bits into a byte before I can send it down. Okay, so this is known as aggregation, where we take many smaller service data units, we glue them together into a larger service data unit before we put on the header here. And then we transmit this as one protocol data unit. And at the receiving end, we split them up into 3 different service data units and deliver them individually to the layer above it. Okay, so this is done for efficiency reasons and also for other reasons. Efficiency is one thing, for instance, because if these are very small and the header is substantial, it's very inefficient to transmit a small data with a large header. So, I mean, think of it as you take the train to Stockholm, for instance. It's not like one person on the train, right? You wait until you have enough people that you can transmit that, because the train itself, which is the overhead, is expensive. Still better than taking the car, but anyways. So we have aggregation and deaggregation. Aggregation. Questions on this? No. Okay. So basically this fragmentation and reassembly, what it does is that it splits it violates a little bit of what we said about encapsulation, decapsulation here. So when we do fragmentation, we split the service data unit into two parts before we do encapsulation. And in fragmentation, we don't encapsulate each of the service data units individually. We put them together before we put them on the header. But otherwise, the principle is more or less the same. As we go down and up the stack, we take off and remove headers as we go along. Multiplexing is when a protocol data unit, so say that this is in layer, let's say that this is IP, for instance. It can then, the IP service can service many protocols at the same time above it. Maybe we have TCP here and UDP here, which are two transport protocols. So both of these protocols can transmit data back and forth using the same IP service below it. This is called multiplexing. So IP supports multiplexing, meaning that it can serve two or several protocols at the same time. Okay, so so the message that goes, let's see, oops, sorry. A message that goes like this is becomes then a service data unit, as is down here, the blue one, and then it's transmitted virtually over to the next entity here, and the service data unit, which is associated with the blue here, comes from the blue protocol here. So say that this is TCP. Then in the header, we add what's known as a multiplexing tag that identifies the protocol above here. So the blue here might mean, okay, this is a TCP packet. And the purple here means that multiplexing tag means, okay, it's UDP packet. So when it comes here, when the receiver, when packets are coming up here, this entity needs to know, okay, should it go through this service access point or this service access point, right? So for instance, if again, if this is UDP and this is TCP, for instance, then IP, when it gets an IP packet, it needs to look into the header of the IP packet to figure out whether it should go to the UDP protocol entity or the TCP protocol entity. Okay. These are called multiplexing tags, and they are put in the header. Okay. One could think that the IP here would just look at the payload and then trying to figure out, okay, is this likely to be a TCP packet or UDP packet? But that's not allowed. Okay. You can never, IP is not allowed to look into its payload to figure out what to do. It can only look at its header. So that's an important design principle. Okay. So many protocols offer this multiplexing where you serve several protocols above it, but not all of them do. In case you only serve one type of protocol here, there is no need for a multiplexing tag because you know when you got it, you know where to deliver it. There is no ambiguity. Questions? Okay. We continue then. Splitting is like inverse multiplexing. And here it's basically, okay, so let's make an example. Say that this is the stream control transport protocol. And here we have IP1 and IP2, two IP processes running here. So a higher layer protocol can use two different versions or two different protocols at the lower end, if it likes. And this is sometimes done to increase data rate or to get some redundancy for robustness reasons. So then service data units that goes like this, then first the blue and the purple one, might go over different protocols below it, right? but then they can arrive at different service access points here. So that's called inverse splitting. So when the upper layer protocol used two protocols at below, it could be the same protocol, but could be different also. Questions on this? No. Okay. I think let's stop here because we have 2 more hours to go, and I can finish off this until we go into the proper lecture 3. So let's take 15 minutes.